In this lecture, we will touch upon a few more ideas regarding the general behavior of conductors and insulators and work some examples. First, let's consider the case where we have a conductor that has a net charge that is non-zero. Let's answer this question. Where would that net non-zero charge be located when the charged conductor is in equilibrium? Let's recall the case of a conductor in equilibrium with zero net charge and no applied external field, meaning no polarization. It looks something like this. The red plus signs representing the positive ions plus bound electrons fixed in position in the metal, and the blue minus signs representing the sea of conduction electrons. A simpler way to draw this is to just sketch the boundary of the metal sample, like this. We'll understand that the ions and conduction electrons are contained in the interior without needing to sketch them. Now, if the sample was positively charged, then in equilibrium, the excess positive charge would look something like this. Namely, the excess charge would be at the surface of the conductor. Let's see if we can understand why. Let's imagine that there was excess charge in the interior, say here. Then, at least in the vicinity of that charge, there would be a non-zero net electric field. But if that were the case, the conductor would not be in equilibrium, and therefore mobile charges would continue to rearrange themselves to ensure eventually that the net electric field inside was zero. The end result would be that all of the excess charges would lie on the surface of the conductor. Later in the course, we'll show this a bit more rigorously using something called Gauss's law. Let's notice one more thing here. If the object possesses some kind of symmetry, then in equilibrium, the surface charge distribution should exhibit that same symmetry. For example, in the case of a metal sample that's uniform in composition and rectangular, like that shown here, then we know that there is one symmetry axis that runs up and down the middle of this figure, such that the left and right sides of the sample are symmetric. That means the surface charges should be distributed in the same way on the left and on the right as shown here. We also know that there is another symmetry axis that runs left to right, again in the middle, such that the top and bottom parts of the sample are symmetric. That means the surface charges should be distributed in the same way, top and bottom, symmetrically, as shown here. Let's try these ideas out on a couple of questions. A negatively charged iron block is placed in a region where there is an electric field downward in the minus y direction due to charges not shown. Which diagram best describes the equilibrium charge distribution in and/or on the iron block? Pause the video and take a few moments to respond before continuing. Let's see if we can eliminate some choices quickly. First, the iron block is a conductor, so in equilibrium, the excess charges, here negative, should lie on the surface. Clearly, this rules out choice 5, which shows excess charges in the interior of the block. Second, we can rule out choices 1 and 2 because they show blocks which are overall charge neutral. They have as many positive charges as negative charges shown in each of these diagrams. Let's do notice here that if the block was neutral, then choice 2 would show the polarization that would be correct with an external electric field that points in the minus y direction. But the block we have is not neutral, but negatively charged. Both choices 3 and 4 depict that situation. However, in the presence of an external electric field pointing in the minus y direction, more of the negative excess surface charge would pile up on the top of the block than on the bottom, because that polarization of the block would enable the net electric field to be 0 inside the block in equilibrium. So the correct answer here is choice number 3. Let's look at this question, which involves charging by contact. The charging sequence is as follows. First, we have two separate metal blocks that are identical in composition. The left one has a positive charge of 6 nanocoulombs and the right one is neutral. Next, we place the two blocks in contact, then allow them to come into equilibrium. Finally, we separate them again. What is the final charge on block B? Stop the video and see if you can reason out the answer before continuing. The key to answering this question is symmetry. Notice that in the middle diagram, when both blocks are in contact, together they form a rectangular block whose total surface charge is the same as that which was originally only on the left block, namely 6 nanocoulombs. The combined rectangular block has a symmetry axis drawn as shown, which means the surface charge in equilibrium must have the same symmetry, the same amount of charge on the left block as on the right. That is, 3 nanocoulombs on each half. When we separate the blocks, each block will then carry the same 3 nanocoulombs, so the correct answer is answer number 2, 3 nanocoulombs. Let's examine another different type of charging that is unique to conductors, a type of charging that can happen without the conductors coming into contact with charged objects. Let's see how that happens. Imagine we start out with two neutral metal spheres in contact, like that shown here. If we bring a charged object, say a positively charged rod, near to one of the spheres, then the electric field from the rod would cause the two spheres still touching to polarize, something like that shown here. Note that the charged rod is not touching either sphere. Now, keeping the charged rod near, let's separate the spheres. They are each now charged, and they remain charged even when the charged rod is taken away, without the charged rod ever making contact. This effect relies on the mobility of charges in conductors and would not work to charge insulators. Let's now conclude this lecture with an example that has two questions. First, an uncharged metal block is placed near a point charge of -8 nanocoulombs. Sketch the equilibrium charge distribution on the metal block. Pause the video and try to sketch this before continuing. The negative point charge is the source of the external electric field acting on the conducting block. So we know what happens. The block polarizes in such a way that at equilibrium, the net electric field is 0 inside the block. The polarizing charges must be at the surface. To sketch this, we should note that the block is neutral. We need to sketch this in a way that the positive charge and the negative charge have the same magnitude. Something like this, where we see for the applied field from the negative point charge, we must have the positive charges pile up on the left side and the negative charges pile up on the right side. These are the most important features that should be included in your sketch. Let's try a follow-up question to the setting. At a point inside the block, 15 centimeters from the point charge, find the vector electric field due solely to the charges in or on the block. Let's consider the point marked with an X inside the block to be a point that is 15 centimeters away from the point charge. We've sketched in here the electric field due to the point charge pointing from the point inside the block toward the charge as we would expect for a negative point charge source. Now we know the net electric field inside the block, a conductor, has to be zero in equilibrium. And the reason why the net field is zero is because two field contributions, the field due to the point charge and the field due to the block as a result of the polarization of the block by the point charge, those two contributions, E sub PC, the point charge electric field, and E sub B, the block's electric field, have to sum to zero in equilibrium. From this, we now know the direction of the vector electric field due to the charges on the block, pointed directly away from the point charge, that is, in a direction opposite to the direction of the electric field due to the point charge. We also know, in order for the total field to be zero, that the magnitudes of these two electric fields must be equal. So we can find the magnitude of the electric field due to the charges on the block by calculating the magnitude of the electric field due to the point charge acting at the point marked by X inside the block. So let's go ahead and calculate that. We simply need to use our point charge formula, where everything is known in this problem. The magnitude of the charge Q, the distance between the point charge and the observation location marked by an X, and the constant 1 over 4 pi epsilon naught. So we can calculate that and find that the magnitude of the electric field due to charges solely on the block is 3,200 newtons per coulomb, where once again the direction of that field, where the direction of that electric field due to charges on the block points directly away from the point charge. That's it for this lecture. In our next lecture, we will pick up a new topic, the electric field due to a distribution of charges.